Yeah, other than that day to turn in the midterm, I was like, oh, hello. Hello, who are you? Okay, so on CCLE, I have uploaded a preview of the final exam. It's pretty much like going to be the final exam, other than I need to finish writing the final, okay? So the finals, there's going to be, right as of now in my head, I'm thinking 4 parts. One will be like you're going to have to write 4 bits of code, all right? Coordinate descent algorithm, gradient descent algorithm, K-means clustering, and E&M algorithm for clustering also, okay? They're all very straightforward. These are all just classic examples of implementing these algorithms. I have written up kind of the task for 3 of those. I still have to write up the task for the E&M algorithm. But I wanted to post this now so you can kind of get started, okay? So you can scroll down. The final exam preview, I think, is right here. Oh, that's, wow. This is the RMD file. This is what it looks like here, okay? So again, it's a preview of the final. I still have to add directions and kind of finalize these directions here. For coordinate, so I wanted to kind of present this, make sure everyone understood what the tasks were. You know, try to clear up any confusion before I publish the actual final. But you can expect the final to look almost identical to this as far as parts 1, 2, and 3 go. And then, and that's it, okay? So I guess I'll start talking about each of these just to make sure you guys understand what's happening. Yeah? Yeah, so it's going to be due Monday, okay? So some of you students were asking for like more time because, I don't know, whatever else is going on in your life, and life is hard and stuff. So I'm going to just, so I'm putting up the preview now, okay? So you have pretty much like 1 week because it'll be due next Monday, all right? So you'll have at least a week to work on parts 1, 2, and 3, and then I'll probably get the part 4 published, I don't know, Wednesday or Thursday. Yes. Yeah. I mean, this is kind of like I'm almost practically releasing the final here, okay? Because the final is going to be, at least parts 1, 2, and 3, I expect to be relatively unchanged between now and when the official final comes out, okay? So the important thing, okay, and we're going on honor system here, and I'm going under the assumption that you guys are trustworthy. You know, if and no one wants to like rat out other students, I get that, but you know, if students are being unfair about this, you should let me know just so it's fair for everyone, right? So so as far as like discussing things, you can discuss things on Piazza, but I ask that you don't discuss with your friends on, or let your friends see each other's code and stuff like that. So don't show your code to any other students and things like that. We're going on the trust system here. You can ask questions on Piazza and discuss things like that, but you know, the way I've taught this class is we're learning how to code a lot of these kind of statistical algorithms for our optimization, and so yeah, I have to evaluate you on your ability to code. So if you're showing other students your code, or you're looking at someone else's code, that's not good, right? I mean, like, why even bother coming to university if you're not going to even bother trying to learn how to do these things? But anyway, so okay, so I'll just talk. I guess I'll read. This is like so terrible. We'll read through each of these things and just make sure we understand how this works. Okay, so let's see. Final exam preview. This is probably a better version here. Okay, so part one, coordinate descent, optimization algorithm used to find a local minimum of some function. And, you know, we covered this last week, but in case you forgot, basically you hold all of the other, you know, if it's multidimensional, you're going to hold all of the other variables constant, and then you alter just one variable, okay? So if you had 3 dimensions, you know, you would hold y and z constant, you would modify x to find the minimum in the x direction, and then once you find the new value of x, you keep x and z constant and you modify y. In this case, we're just going to have a two-dimensional function, a function of x and y. So basically, you're going to hold y constant and modify x to get the minimum in the x direction. And then once you get that value, oh, I guess this should be a t plus 1, okay. You're going to hold x constant and then modify y to change that. So I got to actually, see, this is why I've got previews. I got to update this to say t plus 1, okay. So the question is, you know, well, how do you minimize in one dimension, okay? And there's all sorts of methods. For the purposes of our algorithm here, we'll use a unidimensional minimization method called the golden section search method. Have you guys heard of this before? Oh, okay. Well, I guess we'll cover it now. Okay. So are you guys familiar with the golden ratio? Okay, and what is the property of the golden ratio? Okay, so the golden ratio, all right, let me, I don't want to draw this. Okay, so the golden ratio is that the ratio between x to 1 plus x is the same as the ratio of 1 to x, if that makes sense, okay? Huh? What? It's basically, okay, so imagine a rectangle, and then if you cut off a square in that rectangle, you'll have a rectangle left over, right? So if, you know, you got a rectangle like this, you chop off a square, you'll have a rectangle left over. That remaining rectangle has the same exact proportions as the original rectangle. That's the golden ratio, okay? So we can take advantage of this. Okay, so this is so imagine this is a rectangle with the golden ratio, all right? So here we've got x, x, and 1, okay? Okay, so we have, basically what we're saying is this rectangle has the same proportions as this rectangle, okay? So if I take the long edge, 1 plus x, over the short edge, x, this is the same, is going to have the same proportions as the long edge of this rectangle, x over 1, okay? All right, so what we're going to do is we're going to apply this as far as golden section search goes. And there's a video, I've posted a link to this video. This does about as good as a job as anyone can explain, okay? Basically, here is a function, okay? And the minimum is between, you know, the boundaries of this function, okay? This length d, this is the golden ratio multiplied by the range here, okay? And so by using d, we get 2 new points, x1 and x2, okay? And so as we so as the function goes on, you know, we've got these 2 points, and what happens is you're going to evaluate x1 and x2, and in this case, x2 is larger than x1, okay? when x2 is larger than x1, that means the minimum must be between x2 and the upper bound, okay? If it's larger over here, we can safely eliminate this section and not worry about having to search for the minimum over here, okay? So what happens is we're left with this portion here, okay? And we're gonna basically zoom in here, okay? And the nice thing is that because of the golden ratio, the distance from here to here, okay, and basically from x2 to here, this is basically just scaled down. If I scale this down, you know, this is from A to B and B to x2. B to x2 is about, you know, 62%, 0.618, okay? And then x1 from B is, because of the golden ratio, x1 from B is also basically 62% of the way from B to x2, okay? So the golden ratio allows us to just continue on here. And so once I've zoomed into this portion right here, I don't have to do any more reevaluation. I just have to pick one new point, which is 62% of the way from x2 to B, okay? And I just have to pick one new point, and I don't have to actually do any new calculations because this has already been calculated and this value has been stored. Does that make sense to you guys? And then so I can continue on. I can basically zoom in. So here we are. Okay, so we're going to start here. We've got this point, which is, you know, 62% of the way from here to here, and then this point, which is 62% of the way from here to here. Because this one's larger, we can eliminate it, and we're going to zoom in onto this section. Okay, this section, 3.8, is 62% of the way from 0 to 6.2 is basically what's going on, okay? And so this is already exists from memory, okay? And then I just have to find this new point, and I can continue on the golden search. All right, and so it's just, you're just continually chopping off pieces, and then you're zooming in further and further and further until you reach some form of convergence, okay? So, you know, watch this video, make sure it makes sense to you, okay? And then, so we're gonna use that to minimize our functions, okay? And so, you know, you can read this code. I think this code is very straightforward and simple to understand, okay? And I've basically modified someone else's code to match kind of the notation that exists in this video, right? And so I am already giving you the code to do the golden search, okay? And so the golden search, all it requires is that you provide it a function plus a lower bound and an upper bound for the search, okay? And so you're going to use that as your way to minimize x or minimize y when doing your coordinate descent algorithm, okay? And so to do coordinate descent, we're gonna minimize this function here, and that function has this contour plot, okay? And basically you are going to perform coordinate descent. And so what you have to do is you're going to have to basically write within your loop, you're going to have to write a function and provide that function as an input for the golden search function, okay? Because the golden search takes a unidimensional function and returns the minimum of that unidimensional function. So in each iteration, you're going to have to do, here's the unidimensional function along the x-axis. Here's the unidimensional function along the y-axis. So here's the unidimensional function along the x-axis, minimize it, give me back the value I need. Here's the unidimensional function along the y-axis, minimize it, give me the value I need, and then you continue updating. Yeah. What's that? You only need one loop. You only need one loop, okay? So it shouldn't be too hard, okay? You gotta think when you code, of course. That's always. I wrote up my solution. It took me 12 lines, okay? So, you know, I've been doing this probably longer than you guys have, so I don't expect you guys to use 12 lines of code, right? Maybe you'll come up with a solution with only, you know, 10 lines or whatever. You know, it doesn't take that many lines of code. Or maybe your solution will be like 50 lines of code. I have no idea, okay? I don't expect everybody to be as efficient as I am, and that's okay, all right? But just to give you an idea, it took me 12 lines of code, so it shouldn't be a monstrosity of a task to perform, okay? Is that okay? Yes?
For the golden section function below,
Yes.
and the lower bound and upper bound, do we just put two numbers that one is really small and one is really large?
Yeah, okay, so we're kind of cheating, okay, in that we have the contour plot here. All right, so in real life, you'll probably need to figure out something, okay? But because of this, we're gonna just limit our lower and upper bounds to be negative 1.5 to 1.5 and negative 1.5 to 1.5 over here, okay? So we're kind of cheating, so I'm giving you kind of the upper and lower bounds to search. You know, with a two-dimensional problem, we can just compute every single point and find it, and it's not too bad, okay? But higher dimensions, it would be harder, okay? And so when you do that, and I'm telling everybody to start off in this lower left corner, negative 1.5, negative 1.5. This is where you're gonna start your search, okay? And you're gonna start your search holding y constant, so you're gonna start your search along the x-axis, okay? As far as, to just kind of give you an idea, I want you to produce a plot showing your search. I picked a different starting point, and I performed coordinate descent, okay? So this is, you know, the results of my code, and you can see how it goes down in the in this direction and then goes in the other direction and so on and so forth. Okay, so this is performing coordinate descent, and so your result should look something like this, except starting over here. So going something like, you know, some steps going in this direction, starting in this corner. Okay, so just to give you an idea of what I'm looking for as far as your complete plot at the end, something like this, except of course not this starting point. Any questions on this? Okay, so I'm hoping all of this makes sense. All right, you know, I recommend you start early, just because when you're writing your code, you'll realize, oh, this is kind of hard, or something. You know, early on. It's better to realize that early on than Sunday night. Okay, let's see. Okay, so that's coordinate descent. Gradient descent, we're already very familiar with it from our artificial neural network. You're going to do something very similar, except your function is just, we're going to use the same function of two variables. Okay, and we'll use a learning rate of alpha, and so gradient descent is basically you just calculate the gradient at any current point, and then you just take a step in the negative of that direction, okay? And so this time I want you guys to have a convergence criteria where basically if the absolute value between one location and the next point is less than 0.001, you can go ahead and stop, okay? All right, and so for this one, you're going to start off at negative 0.5, negative 1.5. So you'll start like right here. This is the location that you will start. Okay, and then And what I'm looking for at the end of the day is something like this. Over here I started, so you're going to start over at this point. I started over here and I've performed gradient descent. And this is what happened. And so I ended up down here. Okay? And so you'll use the little arrows to kind of indicate your steps there. Are there questions on this? Okay, and everyone's feeling okay with writing a gradient descent and coordinate descent algorithm? Okay, great. Okay, and then lastly, and so that one I think it took me like, I don't know, 15 lines of code or something. Okay, and then K-means clustering. So I've created. So don't mess with this this line, because this is going to generate our clusters of data. Okay, so these are the clusters of data that we have, red, black, and green here. Okay, and you are going to perform K-means clustering. Okay, and so K-means clustering, that one works by, you start off with some arbitrary or random centers, and then you assign, you associate all the values in your data set to the mean or the center that's closest to all of those. Okay, and once you do that, you recalculate the means of the associated points, and then you perform the algorithm again. Okay, and so I've given you guys 3 initial starting points. You have this center, this black dot, red dot, and green dot, and you're going to assign to this the points that are closest to the red dot to this one. And then so when you do that, I have kind of shown kind of the first few iterations of this. And so the K-means clustering algorithm, it's very fast unless you give it purposely some bad starting points. Okay, so this is kind of the initial set of starting points. And then I should probably make this a square plot. And so with those 3 dots that were here, here, and here, you know, these are the points that were closest to the red dot here. All of these points over here were closest to the green dot here. And then all of these points over here were closest to the black dot that was here. Okay? And then so after partitioning our data set based on those 3 original centers, we recalculate the mean of all of the black dots, we recalculate the mean of all of the red dots, and we recalculate the mean of all of the green dots. Okay, and those are given by these solid dots. Okay, and once we're at this point, we reassign the data points to each of these things, and we're almost kind of at a convergence point where you know, we've reassigned everything to here. Okay. And so this seems like it's done a very quick job of clustering within kind of 3 iterations. And then I think, you know, one more and it remains constant. Okay, and so you're going to write a K-means clustering algorithm to do that. Okay. This one, I think my code took 15 lines, but I had to think a little bit harder about this. Okay, so you have, I mean, when you write something for something like a clustering algorithm, one temptation, and this is totally fine if you can't get outside of this this method of thinking, it's okay. All right, and so one temptation is to say, you know, for I in, you know, every single dot, there's 300 dots, and so you might want to, like, one option is to run a loop, and so for every single data point, you say, find the, evaluate the distance from each of these 3 means, find the one that has the shortest distance, and assign the dot to that cluster. Okay, and then you'd go through that for every single dot, and then you would do that over and over again. Okay, that's fine. Okay. I think it's a lot better to think of functions and think of using the command apply. Okay, so think back to kind of your 102A or something where you've used the function apply to quickly apply a function to a matrix, and I think your evaluation will be a lot faster. I mean, this is a small data set with 300 points, and it converges very quickly, after, maybe like 4 iterations. So anyway, that's what I want you guys to do for that. You're going to, so yeah, after each step, I want you guys to produce the plot, kind of like here, okay? So after the first step, we can see how the data points have moved, and after the next step, we can see how the data points have moved, okay? So at least you should be able to get started on some of these coding tasks, and then I have to finish writing up the instructions for the last task for the EM algorithm, which will probably be the trickiest of the algorithms to write. Okay. Does this all seem very doable? I think it is. Okay, and it should give you some good practice as far as coding goes, which I think is a very useful skill. So, and kind of put this, I don't know, slightly theoretical knowledge of optimization algorithms into a practical context here. Questions? Yes.
This final's due Monday at what time?
So the final exam is scheduled for 11:30 to 2:30 p.m. So I was going to just make it due at Monday at 2:30 p.m. Which is, huh? I don't know what does that mean? Huh? Yeah, another class has a final? Okay, well, just for you. All right, well, I think, so, so I think, well, anyway, I think, the final for this class was scheduled at that time, so I think it makes sense to make your final code to be due at that time, okay? And, that way I'll just say, well, that was the registrar's fault for scheduling these things, and, when you sign up for the class, you're also aware of the final exam codes and stuff like that. So, so I'm thinking it'll just be due Monday at 2:30 p.m. So you should be able to get started, and then the EM algorithm, EM algorithm portion, I'll try to get something. I'll try to get the final version of this, the final thing, published either by Wednesday or Thursday. Okay, and so I feel like it's plenty of time to get everything done. Okay, unless you're like really terrible at coding. And then I would, well, it's probably a little bit too late to question your choice of major, but if you're like really terrible at coding, then yeah, this probably wasn't the best major to have selected, but who am I to judge, okay? So anyway, so it shouldn't be too bad, okay? The K-means clustering algorithm, I imagine that could give some of you guys some trouble, okay? Just because you might have these really terribly inefficient loops. It's fine. If you've got a really terribly inefficient loop, but it performs K-means clustering, I will accept that, okay? You don't have to go for super efficient code, all right? Okay, then I guess with that we can end a little bit early, and then so, yes, question? Oh, I'm sorry, say that again? Yeah, you should, you should always be documenting, kind of just your thought process in the code. Okay, so you should always provide some documentation. And then, yeah, again, please don't show each other the code that you've written, okay? You can ask discussion questions on Piazza. I'm gonna have to change the settings. I know you guys have been, a lot of you guys have been asking questions anonymously, but I want you guys to put your name when you ask your question, okay? And this will just help me kind of get a better feel for what's happening. You can ask questions on Piazza. Again, please don't show each other the code that you guys are writing. All right, and then so, you know, on Wednesday and on Friday, I'll be happy to answer questions about some of the issues that you guys might be facing in as you're tackling this on. And then and I'll have office hours. Well, I've got them right now, and then I'll have them on Wednesday? Yeah, Wednesday from 5 to 6, so. Okay. All right, so good luck. And then, yeah, I'll get the part 4, the EM algorithm posted up soon.